Good morning. Thanks very much for the opportunity. So guys, ROS at CSIRO. For those of you who don't know, CSIRO is Australia's national research agency. We do research in lots of things, agriculture, energy, food, and information technology, whereas our robotics group is. So I'm part of the Cyro Computation Informatics, and the name of my lab is Autonomous Systems Lab, where we do lots of field robotics work and mapping and a few other things like dependable navigation, localization. We've been doing lots of things with sensor fusion. And in all these topics, as you all obviously know, ROS is very, very handy and useful. So today I'm going to talk about some of our projects that use ROS, how we modified some of them, and some of the packages that are available online that you can all check out. And I'm going to talk about the Zebedee scanner, flying version of it, and some other ground vehicles, and thermal mapping system. So if you have any questions at any moment, just feel free to interrupt and stop. It's good to make it interactive. So I'll start with the Zebedee 3D mapping system. I don't know if anybody here is into mapping at all, but this is a system that was developed by my colleagues. The main people behind it were Mike Bossett and Robert Slott. And it's a very, very cool concept. If you see on the bottom there is, let's see if I can I hold the microphone? Yeah. If you see in the bottom there is a little Hakuya laser with a spring and a handle. So what this does is, if you hold the handle, and as you walk around, the spring will swing, and from the 2D Hakuya laser, you're gonna get a 3D scan of the world. It's an interesting concept, and the main merit of this is not only the mounting on the spring, but it's the registration algorithm that lies in the background. So we're still using ROS Forte because this is a product that has been also commercialized, and we did an interesting mobile interface to control ROS and check data quality, and to get that working, had a modified version of the ROS Hakuya laser drivers and the microstrain drivers. So those things improve timing, accuracy, and we had some modified messages. So the commercial version of the Zebedee 1, which is available from 3D Laser Mapping in the UK, has a similar setup, but everything is in a little embedded computer system, in contrast to the previous slide here where you saw our acquisition laptop. I'll show you a quick video of what this does. Just go here. Change screens. So this is, it's easier to understand the concept looking at this video here. Let me just maximize it maybe. So this is my workplace in Australia, QCAT in Brisbane. And this was mapped in 19 minutes, the whole building. So that's my colleague, Mike Bossett there. So you see it's a pretty funny, yeah. So yeah, he's walking around reception, and the point that you see there is the trajectory of the sensor itself. There's an IMU and a laser there, so that's the trajectory of the sensor. So you see all the point cloud around. Let's see. Now I think he's gonna show. Yeah, he's going down the stairs, and it took him about 19 minutes to walk around the site. It's like an industrial park in Australia. So you see there what's going on. It seems like a mess, but the guys do a great job. It's actually, I personally find really amazing the registration algorithm, how they can put everything together and make sense. So that's the final point cloud model. You can see there are some details, 900 meters. And let's zoom out, hopefully. Yeah, so that's the whole site there. You've seen, many people think, oh, this is structure. It works well in structure, but it works really well in unstructured environments as well. So let me just put forward a little bit. So as an example, they did a mapping in the forest, Mount Coota in Brisbane, which is a national park there, Not sure if it's national. So Mike goes one way. Rob's lot goes the other way. Okay, so we have actually two people, two different trajectories, and everything is registered in the end. Let me forward a bit in the interest of time. So you see, that's the final trajectory. So using this device, we've mapped here. So let me close here. Sorry guys, I had a little issue with embedding in the PowerPoint. So using this, continue from current slide. So this is a forest, oak forest in France that has been mapped. This is some cultural heritage sites in Australia. Oops, I have a blank slide there. So you can see that on the mapping of the final results. This is an island in the south of Brazil with a fortress from the Portuguese from the 17th century. That one I mapped myself. We got them mapped in like, I don't know, 15 minutes. And some well-known places have also been scanned. I think you all recognize the Tower of Pisa in Italy. So that's a very cool system that uses ROS. And because, as you saw the nature of it, you walk around with it, sometimes you want to scan things on top of you. So there's a work in process going on of putting the Zebedee system on a quadcopter there. So you see, you can get a high-resolution aerial 3D scanning of the system, and we also use the same drivers, ROS drivers for Hokuyo and the microstrain that I mentioned before, for the IMU, which have been modified. And in this case here, the sensor's rotation is driven by the airflow. So instead of having a spring, the airflow of the quadcopters make the base spin, and you can get, let me see if this video will play, I don't think it will. You can, so you can get, yeah, there's a bit of, that's the setup. You can probably see in the bottom there, the sensor, the laser sensor spinning. So this is a marble quarry somewhere in Australia. And on the results, I think I have a slide with the results. Where's my mouse? So here, this is on the bottom right here. That's what it looks like. So the final mapping. So yeah, the advantage of it, you can map roofs and things that you can't reach, or the other side. On the other side, if you have overhangs and things like that, it's a bit harder to get the helicopter there. But so in this case, as I said before, we have the IMU driver that's also modified, and I have a custom driver for the Eagle quadcopter, and that allows the control flight from ROS. And ground station communication that sends data to ROS, and the ground computer, everything is using RViz there. So ROS is definitely very, very handy in this project. So we also have other projects, Hexapod robot, for example, I'm going to do in time, that uses ROS API for efficient path planning, navigation, and trajectory. So that's one of the active areas in the lab that my colleague, Navinda Kotaj has been working on. And this is one of the projects that I work a lot with myself. It's the Gator Project. We have a camera, stereo pair for vision, and Hokuyo laser range sensors, and a few other sensors there that we put and remove. So we use a lot of Octomap. I think most people who use ROS have heard of it. And 3 degrees of freedom localization on 3D point cloud using a humanoid localization package. And we do lots of sensor fusion using the robot pose extended common filter package. I think in this case we use a wheel and visual and IMUs for that. So you can see some of the trajectories there. One thing that we've been doing a lot is obstacle detection with ROS, where we estimate ground planes and things like that, and to detect objects. And the stereo image processing or the LS ROS are extremely handy for that. I don't know if who works with this topic here, but we've been finding it very, very handy. So we, from the 3-point clouds out of those packages, extract EEMs and get ground plane estimations to detect obstacles in a clever way. This hasn't been published yet, so I'm not going to the details of the other parts of the algorithm that we do here. But yeah, that's another example of how we've been using ROS in our projects. A lot of sensor fusion as well with hyper, spectral, thermal, IMUs, LiDAR. So this guy here, this robot has, sorry, I can see the pointer on my screen, but you can't see there, I'm sorry. So has lots of things that we use the sensor fusion capabilities of ROS for that. And lots of things for RViz, for dataset visualization, and ROS-Spy and matplotlib for 2D, and also 3D data. So yeah, that's another example of another project there. In the interest of time, I think I'm gonna. Oh no, this is the stealth robot. So this robot, we have the goal is to walk around the environment and only move to detect objects. We have thermal cameras on it, and only move when it's adequate to move. Okay, so it's sensing the environment when there are noises and other types of like birds singing or anything like that. So we move so it doesn't distract so much wildlife. So the goal of this is just to be unseen, such that it kind of offers camouflage, but the goal here is just for environmental monitoring. Okay, so that's another platform there with Hokuyos and Grasshopper cameras. We developed, actually, my friend Payman wrote most of it. Payman, more of them. Grasshopper, point gray, not Grasshopper, actually, point gray camera driver using ROS. And it's a very, very good package that's written, and I use it myself a lot. And the Miracle camera there, it's a thermal camera. We also wrote a package. Steve Vidas, who was a joint PhD with CSIRO and QT, he wrote a very nice package. I'm gonna show you the details of the package later for thermal cameras. Gonna skip that. So something that our software engineers have been working on, actually those slides were provided by my colleague Fred Pauling, is Python plus NumPy. It's very efficient and simple for serial drivers. These are some of the lasers that use SICK and ASI, Forecast 3D, and it's fast enough for most serial drivers device, and especially vectorized. And a good thing about it, has simplified communication, and it has a MATLAB-like syntax. So it's very, very easy to use, and has a simple message parsing, and with things like struct there, and NumPy, record array, and simple array operations, slicing views, and it's easy to debug and deploy. So that's something that they found very, very handy. And I mean, I don't know if you have ever looked into it, but it's definitely worth seeing these capabilities. The vectorized algorithm is required to fully leverage NumPy, on the other hand. And compared to C++, it can be more time consuming, more verbose and less understandable. So one thing, if you have little, for example, mini quadcopters, for example, it's not so suitable for low power device, so used in bigger systems where power is not really an issue. So another note here, it's just a side note, what we did before ROS, we had something called DDX. Yes, okay. DDX, sorry, which is Dynamic Data Exchange. So we did lots of our projects using that, and it's actually, in this way, it's extremely similar to ROS. And it was developed in-house as well, and it had things like DDX record, which is similar to the ROS record, and instead of having bag files, it had log files. But the main difference is that it's based on shared memory multicast, whereas ROS is TCP. So there are other transport options available in ROS, but they're not often used. And this shareness was very important when our processors, like in the late 90s, early 2000s, I'm sorry, were not very powerful. For example, we had, I wasn't there yet, but I was talking to the software engineers about it. We had a Pentium 266 for lasers and cameras. So in this type of scenario, efficiency is very, very important. So ROS is, DDX is available online as well under a package called Spring. It's on the CSIRO on our website. It's open source, and some of our projects we combine ROS with DDX depending on what we want. And as an example, in this project here, the HMC project, I worked on this with this vehicle. We combined ROS and DDX a lot for various reasons. And all these other projects, they're all big automated vehicles that were done in the mid-2000s, and they all based on DDX, when ROS wasn't around. So let me just skip that. So Heatwave, that's probably the last, I'm running out of time here. So this is a thermal mapping system. You can see there's a Kinect-like action sensor and a thermal camera there, and it provides maps like that, a 3D color model. Here on the left-hand side, you can see the RGB value. On the right-hand side, you can see the thermal model in 3D. So it's good for inspection, thermal inspection, reconstruction of things, for energy saving, and, well, any other things where you can think where thermal mapping would be handy. For this, I was mentioning a thermal camera ROS package before, wrote by Steve Vidas. You can find it there. If you use thermal cameras, it's definitely worth checking out. It's very handy. It's, of course, free. And I've used a lot myself. It's very, very good. It's just, it's good for the Miracle cameras, for the thermal cameras. So, yeah, worth checking it out if you like. So I'm just going to put my last video here of what I'm Heatwave. Okay, so this is the a video illustrating the mapping. So that's part of the package as well. And we're just trying to, for example, in this structure, find where what is when hotter and colder, basically. But that's it's good for if you want to identify thermal leaking spots or things that are hot where they shouldn't be. And as I said before, energy inspection. So let me see how much time the video has. Almost finished. Yeah, so this is an example. The video should show the final structure in the end. So I can see really. So you can see there on the right-hand corner, on the lower right-hand corner, my friend doing the mapping. Somebody was filming. Yeah, and that's pretty much it for this video. And okay, that's it for now. I have a few more slides. If anybody interested, I can share more things about it. But in the interest of time, I think I should stop. I'd like to thank you once again for checking out what we're doing, and thanks again. And any questions, I'll be happy to answer.